Leetcode 226, invert binary tree. This very famous, or rather infamous, problem from Leetcode, where people on the internet tend to complain about it a lot and say things like, why would you ever need to invert binary tree? It's such a useless problem. Yeah, and the thing is that it is not about being able to just copy and paste the answer to some real-world scenario. It's about understanding of fundamentals, and in this case, understanding of graph theory. Yeah, so it's an entry-level problem for trees, and you can train DFS, BFS, other traversals on that problem, and that's more or less it. It's not about just being able to copy paste it the way it is to some real world scenario. It's about understanding of the fundamentals. And because it's an easy problem, you can pretty much learn everything about inverting binary trees in 5 to 10 minutes, and then for the rest of your life profit from that knowledge. So here is the description. Given the root of a binary tree, invert the tree and return its root. Yeah, so we don't learn from here what is this inversion mean. I will explain it in a second, but we learn about our input and output, and you can take a look on the right side. Input is a root, which is an object or an optional object of tree node structure, and the same is for the output. So we also have optional tree node, and the tree node is that class which is defined above, which represents one of those circles that you can see here, which store the data, the values, or the label, which in our case are integers, and also connections to their children. Here, the collections are only one-sided. They only go in one direction from the parent to the children, and there could be at most 2 children, and this is what the binary is about. Yeah, so binary means that each node can have at most 2 children, and of course they can be none, and they are none at the very bottom. Those are the so-called leaves, those nodes which don't have any children yet. Yeah, of course the tree can grow, and then it grows from the bottom. And for our case, we simply receive the first node, and then through those connections we'll try to somehow go one by one and invert, and we'll learn in a second what this inversion really means, and we will also discuss how to traverse a tree and what kind of options do we have. So now let's take a look at the first example. We have following 3, 4, 2, 7, yeah, and inversion, you can probably guess from this very first subtree, means swapping the children. Yeah, so the left child goes to the right, and the right child goes to the left. That's it. But the same happens to the children of the children. Yeah, so we have to do it like level by level. It's not just to swap the children of the root. We have to go as deep as possible. And here, the children of 2 are 1 and 3. Yeah, and in the output, the children of 2 are 3 and 1. Yeah, so that's the inversion of the binary tree. And we swap the children, but the parents are preserved. Yeah, so every child has the same parent as it has before, just the children got swapped. The one that was on the left goes to the right, the one that was on the right goes to the left. And that's it. And here the second example is even easier version of the first example. And the third example, of course, in edge case where we don't have anything, the input can also be none. Yeah, so this is something that we have to take care of. But now let's maybe copy this and think about ways in which we can traverse the tree. 4 was the first one, and like this, and like this, I think. 2, 7, and 1, 3, 6, 9. 6 and 9. Yeah, that's the input tree. And of course, our input will be just the root, and we can recreate the tree by traversing through the arrows, through those connections to left and right. Yeah, so only the first object will be given as the input, and we will have to go through those left and right connections to discover what kind of nodes there are and how many of them there are, and so on. And we always have two standard options of traversing, and we'll try to use both of them here. So the first one is DFS, where we go as deep as possible and then backtrack. And the second is BFS, when we go level by level. And in our case, we will implement recursive DFS like this, and iterative BFS using additional data structure called stack, or DQ in Python for BFS. But first, let's think about the DFS, which goes as deep as possible, then backtracks and tries again to go as deep as possible, backtracks, goes as deep as possible, backtracks, and so on. How can we implement this inversion? So for DFS, we will traverse the tree recursively. If the current node is none, return plus terminate. If not, swap the children. Otherwise, swap the children, and by getting the result of the recursive call. And that's it. Very short way in which we can solve it, and let's try to do it one by one. So first thing, we would call DFS on 4, and then we would swap 2 and 7, and then we call DFS on 2 and swap 1 and 3. Yeah, and then we call DFS on 1. Here we go as deep as possible on one route and try to swap its children, but they are none. So we simply swap none and none. That's it. And we terminate here since we reached the current node, which is none. Yeah, and then we do DFS on 3. Again, swap none and none, and we can now backtrack till this place and do DFS on 7, which will be exact same thing as here, just 6 and 9 instead of 1 and 3. Yeah, 6, 9, 6, 9. That's it. That's the whole strategy. And we can already implement it in Python. Then we'll go back to train or to talk about BFS. So if root is none, that's our first condition. We return none, or just return, since in Python implicitly we always return none. And then we do the swap. So root left, comma root right equals invert tree on what? Here is left, so here we call right. Yeah, and then we call left here. And that's the whole swap. And by the end, we return the root. That's it. Let's run it. And let's submit. Okay. We pass all the cases. Now we can comment out this part. And try to implement BFS-based solution, which, by the way, those two things stay the same, but what's inside will get a little bit more complex. Yeah, so usually we prefer in such cases DFS since it doesn't require that much code. But to know BFS and its advantages is also a good idea. And since that problem is such an easy problem, we can try implement both ways. And now let's think about the BFS and how to implement it. BFS works with an auxiliary data structure called stack. Create a stack /dq in Python and enqueue the root like this, enqueue. And then while the queue is non-empty, while it still has elements, do the following. The queue or pop the first element or the front from the queue. Swap the children and enqueue the children. That's it. So how will it work? We start, let's make a table like this. We first have the following queue, just the root element 4, and then we pop we swap the children 2 and 7. You already have here, and we enqueue both of them, but after the swap. Yeah, so first goes 7, then 2. Now we pop from the front, so we pop 7. And we swap each children. So 6 and 9. And then we enqueue them. 7 was already popped, so we put 9 and 6. And because we already swapped. And now we pop 2. We swap its children. Here we go level by level. In DFS we went one route till the end. In BFS we go level by level. And the children are 1 and 3. We enqueue them. Like this. And we continue this process. Yeah, pop. 9. 9 doesn't have any children left, so we swap. None is gone. like this. Then we pop 6. 6 doesn't have any children left. So we pop 3. Doesn't have any children left. And we pop 1. And that's it. Yeah, and now we can translate it to Python. So we will need to create our queue. The queue from the root. And while queue is non-empty, we pop the first element. If it's none, if node is none, then we continue. We can't do anything here, otherwise we swap. So node left and node right equals node right, node left, like this. And we append. I don't remember if it's add or append. Let's try append. Both of them. And right, let's see. It was append. So good intuition. And also 100%. So this type of traversal is equivalent to that, in a sense that we get the same result. But of course, under the hood, we use different strategies.